So the basic things I want to bring up is framing questions in the context of decision support. A lot of people here are doing that. A lot of people have given talks that were doing that. But we, as a subject, and especially in our teaching, don't do that. So I just wanted to spend some time really talking about that framing. A little bit of time on resilience, and then you get to raise questions for discussion. So this is a slide that Peter March used a long time ago when he was head of DMS at NSF. This was an introduction to sustainability right at the beginning of the 2013, the planning process for Math of Planet Earth 2013. So he was making the point that all these things are involved in sustainability, and that the role of math can be to bring coherence to all these subjects, that we can be the translational language between a lot of these subjects. I gave this talk at the Carriage House in DC to the MAA. I mean, I included these slides in a talk. And a woman came up to me full of indignation at the end and said, no, it's geography that brings these subjects coherence. And of course, whatever your passion is, you can bring coherence to these subjects. And I think that's really important for the point of view of education, to teach our students that whatever their talent and whatever their passion, they can focus them on questions of sustainability if they choose. In particular, it needs interdisciplinary courage to address these questions. And that means courage in the students to translate between all these disciplines, and courage in us because we don't have that interdisciplinary skill. Right? Most of the students' teachers were not trained to have this interdisciplinary skill. So somehow we have to facilitate the students learning that skill even though we don't have it. There's an example. Yesterday at Bowdoin, there was a teach-in across the entire campus bringing together intersections between, connecting racism, climate change, and social justice. Don't know if you can read this. Please join the campus community for discussions, open classes, and panel presentations made by and for students, faculty, and staff. We hope that this will be a day of discovery where we evaluate the human and financial costs of action and inaction for all the stakeholders on Earth. So it's the first time in my 10 years at Bowdoin that we've had a teach-in. I told all my students this was the most important day on campus that I'd been there. And I'm not there. It was yesterday. That's certainly an educational thing we can do to make our students, help our students think much more broadly than any of us think. I also feel that it's really important that when we're thinking about educating our students, we empower them with hope. We don't paralyze them with doom and gloom, right? Okay, so then the decision support framing. I like this thing by the National Academies about what is decision support and how to inform decisions in a changing climate. Collaborative production of decision-relevant information and its appropriate use. To help me think about how we do that in a non-trivial way, I like to think of an analogy with math biology. A lot of us in this room are very comfortable with math biology. We understand that there's a bridge between math and biology. And those of us who like math biology can situate ourselves at different places on the bridge. Right? So we can be down here at the biology end, immersing ourselves in a lab, working with the biologists, communing with the data, figuring out all these things, what can be measured, what can be controlled, what's the source of uncertainty. Or we could situate ourselves somewhere more in the middle, where from these models we're extracting the structures and we're studying the different structures that arise in biology. So oscillators, excitability, bifurcation, of course, this beautiful balance that nature walks between stability and adaptability. Or we can situate ourselves even further along the bridge, and we're proving theorems and developing methods. And it's fine, we need the whole bridge. And that bridge creates a two-way stimulus between the subjects. So in my trying to think about how do we frame this, let's put decision stakeholders there instead of biologists. And now we have a bridge between math and decision stakeholders. What's different? We are working with stakeholders. We've added the question of what's the cost in a much more overt way. And all these structures underneath still arise, but we get new structures associated with cost and with resilience, which involves characterizing disturbance. But we still could situate ourselves anywhere on the bridge, and we still have a two-way stimulus between the questions, the subjects. So in math biology, in order to build this bridge, 10 or 20 years ago, we were working really hard to build this bridge. And so how do we do it? We wanted to increase the overlap between or among individuals on the bridge. So we wanted to increase the radius of individuals on the bridge. So we came up with all kinds of ways of doing that. We've got societies, we've got institutes, we developed funding initiatives, we thought of educational initiatives, we run workshops, and so it goes on. Jane was talking yesterday about what they do in England with industry, and they run these study groups, and they have industry institutes, and we have SAM. So we also try to do this with industry. It's what we're doing with the Math and Climate Research Network. Again, our goal is to just make it easier for individuals to increase their radius across the bridge. So then the question is, I think one of the questions we're really asking here at this workshop is, how do we create opportunities for individuals to increase their radius between math and decision stakeholders? So that's what MPE 2013 was about, the plus, that's what we're about. It's what the SIAM activity group on MPE is about. There are already societies, of course, the Research Modeling Association is about that. Statisticians already do this, engineers already do this, economists already do this, climate scientists already do this. I just don't feel that mathematicians do it much yet. So an example that I'd like to share with you about food systems is, while I was on sabbatical in England, I was casting around trying to figure out, how do you talk to decision makers? Here I am saying we should do it. I had no experience in it. So I was just casting around, talking to everybody I could about how you talk to decision makers. And I found this guy, John Ingram, very, very helpful to talk to, very interesting. He runs the food systems program at the Environmental Change Institute in Oxford. And this is the small goal of the food systems program, right? Sustainable food and nutrition security for all. So let's just explore in there a little bit how we did some bridge crossing with this example. So I've borrowed this slide from John. His definition of food security, well, the World Food Summit definition, is that food security exists when all people at all times have physical, economic, and social access to sufficient, safe, and nutritious food to meet their dietary needs and food preferences for an active and healthy life. Something that he points out very clearly is that sufficient here should be interpreted as sufficient and only sufficient. This definition is universally applicable. It refers to more than just food production, and it's underpinned by food systems. So what does he mean by a food system? This is what the food systems community is doing without math. So they're really trying to build a model that doesn't yet have math in it. So and you read it from the top. So what's going on at the top? 3 billion people are in the green zone of sufficient calories and sufficient nutrition. Approximately 1 billion have insufficient everything. Another 2 billion have calories but insufficient nutrients, so they're all unhealthy. Another more than 2.5 billion have too many calories and often insufficient nutrients. So there's about a third of the world's population are food secure by that definition. And how are we figuring out what where they're getting this food security or insecurity from. It's about what goes in their mouths, right? So a lot of foods, when people are talking about food, they focus here at the producers. And the point that John is making is that there's the whole food chain system, there's all the processing, packaging, trading, shipping, storing, advertising, retailing between the producer and even what may or may not be accessible to the individual. Up at the individual, there's affordability, preference, social norm, cultural norms, convenience, etc. So this is what he means by the food system. And the questions are, and of course these all feedback on each other, there's feedback everywhere, it's this huge, massive, terrifying model, right? With climate change and land use playing huge roles as well. But this is what he'd like to think about. And you can't just think about it in the abstract. So the other thing he's done is led this group that's finding priority research questions for the UK food system. So he's definitely working with the policy stakeholders. So I'll just show you some examples. These were the top 5 policy questions that came out of a stakeholder group from the UK government. So these are the top 5 questions the UK government would like answered. For example, how can UK food supply and primary production adapt to more extreme weather events? Which UK groups are likely to become food insecure in the near future and why? So that's the decision maker questions, the government questions. There were top 5 from other stakeholders. This is NGOs and advocacies, and I just put a couple of each so you wouldn't be reading forever. But how can food prices or other financial mechanisms account for environmental and health externalities in food production and consumption? It's a question a lot of us are asking all the time, right? What dietary choices would UK consumers make if their intake of meat and dairy products was reduced? We hear a lot that we should reduce it. If we did, what choices would we make instead? How would that impact health and sustainability? That's what the NGOs want to know. Primary production, the harvesters, the farmers, the fishers, what do they want to know? How can the sustainability of UK primary production be improved without expanding our social and environmental footprint overseas? How can primary food production be sustainably intensified while maintaining or enhancing the nutritional value of these food items? So why do I include all these? As examples of actual policy questions, right? Most of the modelers I know are this group not included. This is an unusual group. But most of the modelers I know are very, very far from thinking about actual policy questions. And of course, thinking about that bridge, where's the math? How do we extract the math from these questions? So this was one of the places where it was really useful to have a network. I have a network. So I went and met John. John and I have interests in common. So this guy who's got a food systems network and me who's got a math climate research network can bring our networks together very easily. It's not just 2 individuals trying to fight this big war. It's 2 people who have 2 networks that can come together. The food systems overarching goal is this hierarchy of models of food systems. It's rather like the climate modeling goal of a hierarchy of climate models. Why? For scenario testing to inform intervention strategies, right? In particular, I have to write this down because I can never, using modeling and data and behavioral economics, using those 3 together as parallel and synergistic qualitative and quantitative approaches to scenario testing for policy. Right? So we ran an AIM workshop. And the goal of the workshop was to focus on the US food system in particular, to identify math challenges driven by policy questions, and to build community. So there we are. A whole bunch of the Math Climate Research Network here, a whole bunch of the food systems people here, Also people from the World Bank, people from industry, people from Nestle, really trying to bring this group of stakeholders together to mathematically enrich a social science style participatory process. So we chose, on the first day we spent struggling to define the food system. The second day we spent making up some policy questions. What did we think were the most important policy questions to address? Not because we thought we were the experts in figuring out policy questions, but because we needed policy questions to focus our model building. So we chose these three for the three teams to work on. And then we looked for the cross-cutting themes that emerged from trying to address these three questions. We did a lot of this. So here's a lesson that I really learned, which again a whole bunch of you guys know. We did a participatory process where we're mixing qualitative and quantitative information. Hard to do, right? Our sessions were facilitated by quantitative social sciences. I don't think there are very many of these people in the world. I could be wrong. But it was essential that we had these individuals who could communicate. They were already bridge crossers, right? And they could communicate with those of us who like quantitative stuff and those of us who like qualitative, and they could help us bring those ideas together. While the mathematicians were more or less not eager to bring in qualitative information, and vice versa. So we did a lot of this, sticky stuff and brainstorming stuff, and confronted the fact that each set of experts yields a different network, of course. That's okay. We know that all models are wrong, that some models are insightful, right? We all know that. In terms of education, what skill should be teaching our students? Ever more vigilance in the translation process from application to model. We do this to an extent, but even more vigilance. And I think at the level that we're talking about, what should we do with the high schools? What should we put in modules? More word problems about policy options could begin to build those ideas. What else? Each policy question yields a different network. That's not surprising. We should be building models that focus on the question, right? So what's the educational message? When we're building models, when we do this for biology and for experiments, we build a model to help design experiments. We want to distinguish between experimental outcomes. In this situation, we want models that distinguish between policy options. And just at the research level, what kind of math was emerging? The cross-cutting theme that we saw in all the questions was that we have a combination of differential equations, agent-based models, because we're always talking about human and consumer choice when we're thinking about food systems. And we need some robust optimization, and we're doing it all in the framework of uncertainty. And so bringing together these three types of model, or these three types of model with robust optimization. It's been nice for me to find out that there are people here who have thought about even bringing these together before. But it's not common yet, I don't think. And they were just cross-cutting through all the policy groups, those themes. Other cross-cutting themes were how do you use qualitative information from subject matter experts, and how might you start to check that qualitative information? And we had somebody from IBM, so she was all about creating massive multiplayer online games to see how people respond to qualitative choices, so to check those behavioral choices in food systems contexts. I just want to say two more things. In my work in math biology, I've discovered that these are the magic words. If I want to find out what the biologists are really struggling with, where's the good place to model? Those are the magic words as I was trying to get in the door of policy people in England. I was trying to talk to people who work in government, civil servants. Those were the magic words that suddenly, a mathematician comes to talk to them, they have no interest. Till I said that, and then suddenly they were all interested. I don't want to keep us late, so maybe I won't talk much more about quantifying resilience, except to say that it's, what do I have after here? These are, I like these books very much for helping us think about resilience. Especially this book I've used in teaching. So I've taught a modeling class using this book. It doesn't have a single equation in it. But the goal of the modeling class was, I used both of these, but when we were using this book, the students had to build models, had to build resilient models in which they could think about quantifying the resilience of the examples described there. What they're describing here is a whole bunch of alternative stable states, systems with alternative stable states. So we thought about the definition of resilience. And then we thought about this, what happens if you can think about resilience to a single disturbance, and then in the math language it becomes the size of a basin of attraction of a state. But if you're thinking about resilience to multiple disturbances and possibly changing disturbances, then it becomes a question of the interaction between the attraction in the state, the attraction to a state, and stochastic disturbance. So it's this interaction between the strength of the attraction and not. You do that under a changing environment, under climate change, and you start changing the parameters of your system at the same time as you have disturbance. This, for many people, this says, oh, well, you're looking at stochastic ODEs, and we have a big, huge, beautiful theory of stochastic ODEs that says you will always escape a basin. You're always guaranteed to lose your resilience. That's based on the assumption that your disturbance is Gaussian, has tails, has long tails. But if your disturbance comes from a compact domain, then that may not be true. You may well have resilience in the sense that you may stay within a basin of attraction for all time if your disturbance comes from a compact domain with a frequency that you have some estimate over. So I think there's plenty of room for very elegant research in there. And then the other point about resilience is that within the ecological world and within the world of biodiversity, right, systems are not at an equilibrium. They're hanging around in a basin of attraction of some kind, being disturbed all the time, like a forest with its forest fires. It's the disturbance that maintains the biodiversity, right? So even our usual way of thinking of the state is the attractor, how strong is the attractor, is not capturing what's going on very often with resilience. It's some region of the basin of attraction that is the state that we want to be in. And so it's the resilience of the basin of attraction that's interesting. And so it begs again the question of transient dynamics. Focus our research on transient dynamics rather than on long-term dynamics. And the interaction between transient dynamics and disturbance. Okay, I should stop. Thank you. Yes, Lou. What a surprise. Yeah, we should let Christian go first.
Okay, one comment. It was very interesting when you show your food system. There was one ingredient that I didn't see, and in fact for me is very important. There was a report from the United Nations, September 2013, which
Yeah.
says that 1/3 of the food in the world is just wasted. It goes
Oh,
to
yeah.
the garbage.
Right.
And so it's not just a question of how we produce more food, but how we don't
Yes.
waste. And in fact, last week in Montreal, I couldn't find a reference on the web, but there was an article saying that half of the fish in the United States just
Is
goes
wasted.
directly to the garbage. So
I
it's
think
really a question of how we reorganize so that we limit the waste.
waste was in, this is supposed to be top 5, I just cut 2 of them.
Yeah, okay.
Waste certainly appeared in
Okay.
those top UK questions.
I had a comment on one of your first slides where you
Mhm.
had saying math is making the...
Oh yeah, math
And then you
brings
said it was
coherence.
very controversial. I think we shouldn't say math is doing it. We should say math is contributing to doing
Yes.
it. But there is room for geography. We couldn't claim that we are doing
Yeah,
it
absolutely,
completely.
of course,
We
yes.
should be,
Yes.
and in fact, okay, maybe math is essential for doing it,
Mhm.
which doesn't mean that we
But
are...
the others are not also essential for doing it
Exactly.
right. Right.
Lou, did you want to go?
So thanks. A couple things. One is that when you put up that basically the distribution from math to biology.
Oh yeah, the bridge, my bridge.
Yeah, the bridge. I immediately said, okay, we should view this as a stochastic process in which some of us spend certain fractions of our
Yeah.
time at different points on
Absolutely,
that bridge.
we jump around
And-
the bridge.
And dynamically, I think this was pointed out in one of our, was it Carlos, maybe, who pointed out that everybody that he mentioned, Simon Levin and
Yes.
Alan Hastings and all, jumped across that bridge as various points of their
Right,
careers.
right.
And so there's a dynamic and stochastic component to that bridge. So I
Yeah.
thought that was really cool. Thank you for
Yeah.
showing that. With regard to decision support, though, so I will add an addenda that there have been enormous numbers of decision support systems built by
Yes.
geographers, by engineers, by math folks, by all
Math
kinds of
folks.
math folks too. Yes, mathematicians we'll call it. Supposed decision support systems, virtually not, and NSF has supported enormous numbers of these. They call them problem-solving environment. There was a whole huge effort on this years ago. Virtually none of them are useful for anything. Okay, and the reason is that in many cases, the process of deciding on the key questions did not, at the very initial stages, involve anyone who was a potential user, and they were
Right.
not involved throughout the entire process of building
Exactly,
them.
that's my point. That's
So-
why you've got to work with the stakeholders,
Yeah,
the users.
and
So the mathematicians can't do anything valuable, truly valuable, if they're not working with the users, and the users can't create a model that's going to be mathematically tractable if the mathematicians aren't involved at the beginning.
So just that one should potentially, before investing time in one of these things, sit down and look at the cases of decision support tools that are actually being used in sort of the discipline area that you're talking about.
Right.
And so I don't know what is used with regard to food security, except for what goes on here with regard to very specific aspects of risk assessment in food production facilities.
right.
And there is a
Which
whole
is-
set of decision support tools used for that. But in the broad cases of the issues that you're talking about at much broader scales, I'm not sure that there's anything that's really
Absolutely,
used.
right, right.
Any other comments? Okay, thank you very much.
Thank you.